Hello, my name is Carlos Ordonez, and I'm going to do about the seminary from the course Differential Equations 2. Today I'm going to expose about the topic, boundary value problems. Also, I need to mention that I have my notes here because in previous recordings I have messed up some kind of definitions, so I come here to remember those a little bit better. Now, what do we have to develop now that I have said that we are going to see boundary value problems? Well, we are going to specifically be checking the cases of boundary value problems with the second order and nonlinear equations, which is the case we have specifically here. Excuse me. Let me. This one right here. This one of the cases we are going to be analyzing and moving all around the video. So now, let me write this one right down here because I'm going to need it later. Specifically, the kinds of problems we're looking for to solve are these kind of problems. When we have x prime equals to an if x, and also it has the conditions, we can say in that way, where, for example, an x evaluated on 0 equals to an x evaluated on b, and these ones are evaluated on these two are also equal to 0. Also, I'm going to mention that I'm watching here that the recording and everything is okay, because I have also suffered from that one recording mess up, so I'm also checking that. Okay, now I mentioned that this is the type of problems we are wanting to solve. Now let's see what kind of definition we have, or what kind of details do we have. So first of all, because we are usually familiarized with this type of problems. I mean the higher order systems, where we know that usually what we do when we are doing with higher order system, what we do is this type of change of variable. I mean this one. For example, we take the x prime equals to y. We do this change of variable to make it simpler. How do we solve this problem? So this is the first thing we do. Then we are also working with one curve of energy, or that's the way we are saying this way, and also this curve work with equation in this way, and this curve is described this way, okay, and goes with equation from 1/2 y minus this one we are calling the big F because it's simpler to us to understand, evaluated on x, and this one equals to a c, where this c is going to be the energy, right? Well, something else that I need to mention is this big F that we have here is specifically this F we have down here, but it's not the same. Basically, this F right here, the big F, is defined this way. The big F is actually defined as the integral from 0 to x. That's as usual. We have the little one. Sorry, let me erase this. I forget. I need to mention this. This actually is the same function. Is the same fx that we have right here, but right here we are doing this thing right here. So we need to do we need to take another variable. We don't have a lot of variables, and to make it simple for us, we do the one that is usually the most common, that is s. So we put here the s and the s. Simpler. It actually this looks like a 1 x. Yeah. Also about the curve that I said before here, we have this curve is not an empty set, and also it should not contain singular points. And also this curve actually carries or contains most of the solutions that we are looking for systems. So with that same, well, for our system, what is our system? Well, we define it right here. And usually, how does a curve looks like? Well, for the way it's defined, looks like a circle in that way. But we usually take, for example, we usually take this curve right here, which is actually half plane, or that's the way it is defined. And with this part of it, we have especially a figure in the book provide us from one figure of to know or to look how is actually the curve looking. So that's what we have here in this part right here, the part A. Let me use another color. Yeah, as we can see here, as I said before, this curve is actually a half plane, and we have two endpoints. The first one that go for 0, GC, and GC that is fine right here. This GC, as we look in the picture, as we look in the figure, this GC needs to be bigger than 0, and also is minus GC, the same. And also in 0, because it's a half plane, there must be a point that of a curve that intersects on the x-axis, because we have a minus and a plus, and we know this is continuous, does not have singular points, all that stuff. We know that, so must have this point right here that we actually call it 0 and x this way. Yeah. Right now we are not looking that much on the figure part. In the part B of the figure, we are looking that later, but it's also important. So we are coming back to this a little bit later. Yep, that's what we already have from the figure and the curve. So now, what information do we have from that? Well, uh, we have these parts, but we actually what we really want to know about this stuff is actually, well, let's see that for example, we have uh, this. Let me separate this part because we are going to talk about a different part. Now is where we are going to start talking about this part of the problem, the figure B, because as I said before, now what we're looking for right now is a solution, XCT, yeah. So now let's consider, for example, that we are looking for the half of the time. I mean, let's consider this. Let's call it TC, and this TC is actually the time that for example, let's call a particle that the times that it needs to go from one point to another point. Which points we are looking for? Well, from specifically we're looking for this part here to here. Yep. I think I jumped something. Sorry. I think did this too early. Yeah. I jumped something because I want to go that way. In continuing with the figure A, sorry because I'm jumping some because of I missed this part on the notes. Well, I have this part right here. Without loss of generality, do we have, for example, as I said before, this curve right here contains or carries covers the solutions from the system. So let's call, for example, that we have a solution for an energy C, whatever we wanted. For example, let's call it XCT, because our solution is going in C. Is based on T. It doesn't the independent variable. And also we need to focus that we are talking about autonomous problems, so autonomous nonlinear boundary problems. So yeah, that's why our independent variable is t, but actually it's not mentioned on the problem. For example, right here we don't have a t, but we know this based on t. Okay, let's say we have the solution xt for a c anywhere we want it. So what do we have according to what we already know? Well, from the curve, we know that, for example, xc, this curve on 0, it must be 0. Yep, in that part, the solution don't vary mostly at all. Why do we know that? Because of the initial values we have. And also, let's say that we have GC, and from this one no, for this one let's say 0. And what is this one? Well, actually this one goes to GC. This is the part right here. These are those points. So yeah, we are having those points right here, and also we are looking for these points right here to make this second curve. That's the solution that we already said. Yeah. Now let's consider, for example, that we say that we have that solution xct. We talk about that. Now, for example, let's consider, as I said before, a time tc. I'm putting this right. I'm putting this later down to don't confuse myself. Let's say we have a time tc, which is the half of the time of all the travel from this particle. Let's say it that way. I'm the way I learn in the best way possible is when I remember when I was in primary, with all that stuff we learn in physics about parabolic movement, all that stuff. So yeah, it's a time that, for example, to our particle to go from one point to another. Which are the points we are looking for? Well, it's just a half point. No? This is the TC we are mentioning. I'm going from this point to this point. This is a half of everything. So also we have times 2 TC. Yeah, I'm going to put this down below because I need it down. I need it there. Okay, let's say that we have the time TC. And let's say, because as I mentioned, well, if a time, we consider as a time, so this is going to be positive, first of all. Also, let's say we have our, excuse me, I missed something again. No, right? No, yeah. No, I don't miss anything. Yeah, because the time we are saying this one is positive. So later, what do we have according to the graph that we already saw? Well, we have this part. This is the solution, or the part of the solution we have. And from TC, well, this one according, because it's like a parable, I don't know. Yep, we have this part of it. It will be the XC that we have from this part right here. So also we will have this part right here that you see from this part in TC will be also 0. Yeah, that's what what we already know and what we have. Now, as I mentioned in the beginning, we usually do in this type of problems, we do this kind of change of variables. So now we are not actually going to use it, but a little bit later. First, we are going to use the way the curve is actually defined. So we are using these two. So now first I'm going to write this one. Why all this? Because we are actually we want to look of this. We want to evaluate the time. So first we write that down below here. Equal to C. As we are supposed we have a solution for a C anyone we want. We are supposed that we already know what is a C, no? Well, no. Sorry, I'm mixing Spanish. We have those. So what do we do? Well, we already know this part right here. We can just move this part right here and separate all that expression in this next way. We have, I move something, I don't know what I move. Okay, I don't move them. We have C plus fx, all this multiplied by 2, and this is the square of this. Now, y, this is not y, is y. Y will be equal to this way, and 2c plus 2fx. This is what we have. Now, we are talking about, for example, the time, and so because of that, we are actually saying that, for example, the Gx what you have. What is G? Well, G is defined as of all this. But looking at this, for example, in this part right here, what are we doing? We are going up, so the derivative, the x prime of this, should be bigger than 0. And in this part right there, this part should be negative. So that's why with this, we know that because it's a root, we have plus and we have minus. So we are talking about this. First, we're looking to this part. So first, we are taking the positive number. I'm going down here. So first, we are taking y as a positive from 2c plus 2fx. Yep. Yeah, that's what we already have. Now, I already say we are also going to use this. We already use it, but we are going to use it more right here. How do we use it? Well, this way. As I said before, we want to evaluate about the time. We want to know more about this. And what do we have? We have x prime. I'm going to separate this because to not mess up myself. X prime we have equal to y. Sorry. X prime, we're using all these differential stuff. We have x prime must be equal to dx over dt, right? But this we can see also as dt, moving this stuff, and it should be equal to dx over x prime, which is also dx over y. I don't know why is this here. I think I write it pretty ugly. Let me repeat this. We have dt equal to dx to y equal to dx equal to x prime. We have this equation right here, and we already know this part of y in this part of the time, right? So what do? We now just replace. We replace that part, and also we need to do it we replace this part, and we don't want to know about the differential time. We want to know about the time tc. So what do? we integrate both sides of equations. So what do we have? Well, for the first part of the equation, we have from 0 to, we want to know about TC. So this goes, the T goes from 0 to TC. That's what we already have here. As I said before, to understand this part, I really based on these two graphics right here. We have this is T, and we go from here, to TC. So we integrate all this stuff, all that part. 0, okay, 0 to TC. And what do we integrate? That's what we have. And also in this part right here, where we have from 0, and this part we don't have actually, this is not the same as in here, but we have this part here. And so what do we take? We take from 0 to xc. That's a limit of the integral we take. And also we just replace, as I said before, we have dx over y. It was defined as the positive square of 2c plus 2fx. Yep, that's what we have. Now we just solve a little bit this, or make it simpler or easier for us to understand it. This part right here, we already know this one is TC. I don't think I need to expand on that part. And this one right here, actually, because I don't know effects, not yet, because this is just the definition of this part, we just let that integral express in that way. But also we reduce a little bit. How? Well, this two right here is on both parts of the sum of the expression, so we can use common factor. I think that way is so we do that. And what do we get at the end? Well, we get this 1 over 2 there, well, 1 over the square of 2 dx over c plus fx. The same thing, but a little bit easier to understand. Yeah, this one, because it's actually do not have variables, we can take it out from the integral. So yeah, we click on exclude it. I have this part, the integral from 0 to x dx, just to make it easier for us to understand what we have. C okay, c plus yeah, we have that part. That's our TC, or least expression we already obtained. Now, actually, the book continues, with one lemma that I'm going to explain also, because I actually consider it was necessary, because it's also about this expression right here, and it gives us a condition of when this expression actually converges to a finite point. I mean, it does not diverge or go to the positive infinite. Okay, this is a lemma. This is a, why is this? Okay, I don't care. This is the lemma we have. If the xc, the point, is not a singular point, then tc must be finite. I mean, this tc should be integrable. That's what we are saying. Let's remember that tc was I put it right here, because we are going to actually also we are going to need it. 0 to xc. Yeah, that's what we have. And what is the lemma saying? The lemma is saying that basically they are saying that this is integrable. they are not saying more than this. So what do we do to prove this? Well, actually, something more that we need to know is about the singular point. The singular point for definition is when is a point where the function is actually continuous, but it's not derivable. So, for example, in previous courses of calculus, we already saw this type of function where the most common that we at all time we see is the type of functions we have like this kind of roots, or how do we say that? Peak, uh, that they change they change their slope in a very drastic way, so they have this point right here, and this point they are not differentiable. So yeah, but they are continuous. So this one right here is called a singular point. Okay. Now about the lemma, what do we want actually? Well, following with the proof that actually the book gave us, and I consider was a good proof, I I follow it a little bit easier. I don't lose a lot. They use the expansion of Taylor. They use all that part. We already saw those on previous course of calculus, so I want to just do it basically. And they use the Taylor expansion of this expression right here. They use the the big F, but evaluated on the point xc, which is the one we know is not a singular point, plus a c. And also they make equal to a 0. That's what we have. Okay. They make that expansion of Taylor, and that what do we obtain? Well, following the definition, basically, we have this, and also plus c. This one is now we see why they use this, because they want to obtain this part right here. They want to obtain that this expression right here to make it easy for us to know how to integrate, or what the result of the integral will be. So, what is expansion of the derivative of the part right there? Well, it can be looked as this one, because the center, or what we call the center, is we have the derivative of the big F evaluated on xc, and minus, well, I multiply this one from the point x minus the point xc, and all this by a residuum. I don't know how they call it in English. This one right here. Okay, that's expression we have for the Taylor expansion. But as we say at the beginning, I keep this here. Where do we have? Where do I have it? This is the integral of from the previous result from the course's analysis. We already know that, for example, and also from calculus, we already know, for example, that if we take the derivative of this, will be actually the needle left right here. So we use that result, and what do we have here? Well, we just have the next thing. This plus okay, that's what we have. So now, because we are actually not looking for this part, we are actually looking for this. We are actually not looking for this part right here. We are actually looking for this right here. So this is basically doing all the stuff right there. So we know that we know x0 it's not a singular point. So this one right here, it actually is different from 0. Yeah, this one right there is actually different from 0. Basically this one. This fs is different from 0. So because of that, all this expression actually will be different from 0 first of all, and also will be integrable. And that's what we needed. I mean, this integral, because of the way we know the all this part is defined. Well, because of that, this part right here will be integrable, and that's what we need, as I said before. Yep. Actually, that's the proof that the books tell us. So now, that is just to say that actually this is not going to diverge in this part right here. So now we can continue with the next part right here. I'm going to do it here because I want to go next to I want to continue with the figure, using the figure. I'm going to separate this. Let's go to the beginning. As I said before, first we have this part right there. First we use this first part from DC. Now let's consider, for example, another variable. This one could be anyone. I mean, it doesn't care. For example, the book, they call it in this, I think they call it a TC. For example, I will call it just T1C, just because it's simpler to me. When I do my notes, I do it in that way. Yeah, and what are we representing with that part? First, we call TC this part right here, and now we're going to call the D1C the other half of that part. I mean, this part right here, when the effects go, when should be lower than 0, as I said before. Yep. Well, we have it T1, C. And as I said before, it goes from that point from the XC, I think, goes from the point to XC and to the point GCT. So from this point to those points goes. No, sorry, mess up. According to the function we already saw, goes from XC0 to the point 0 to YC. This one is in the curve right here. I mean, we go from here to here, and from here we go this XC, as I said before, XCT, so to this XC to C, but we already call it as a GCT. So now we are basically, to be more specific, to be more simple to us, we're working with these two. These are the 10 points we have. These are on the curve, right? This part right here. Okay. Okay. Because we already say that this part is actually a symmetry, we know this one T1C is actually going to be equal to the TC that we already look for. But also, we know, as I said before, that this time TC T1C will be a little bit different in some part. Will be a little bit different in, just in a tiny detail. This detail will be actually that y, should be in a negative, will be in the negative root of that part. From that's the only detail that actually changed in this part right here. So we have this TC will do actually do the same. And also we have the or TC is a little bit different because it does not go from, as I said before, in our previous one, we go from 0 to x0 to xc. Now we're going from xc to 0. So we are actually going to change in that part right there. But our time is the same because we know it's the same time right here. We have that part here. So for example, to the first part of the, we are actually going to don't miss. I'm going to repeat the same process. I mean, I'm going to repeat from here. To don't get lost. Why? Okay. Now, when we integrate this, because we have the time is the same, so we can do actually the integral in this first part of the equation. We can do it as T1C. T1C is actually TC, so it's basically the same. What do I mean? Well, and dt, we are going to tell T1C, but we already know this one is the same as CC. But for the other side, we have, because the way we are defining y is minus, and also we are going from the xc to 0. So the limits of this integral are actually in the opposite way as we did it in the first one, right? So, but that's the point, xc to 0, and we have dx over y. As I said before, that's the point because we have, because of properties of from the integrals, we have seen this from calculus previous courses. I think also in analysis we already saw this. That, and let me put this one right here. It's used like a remember myself. Well, not myself. We have an a and b and dx. Then this one should be equal to minus ba dx. So, well, with this one, actually we have basically everything. Why? T1C will be equal to. I won't make use of this right now. Let's replace the y to don't get lost because I can get lost very easy. So the y, as I said before, was minus 2c plus 2 big fx. And this one, now let's make use this property. So now minus minus they go plus. Then we have c to 0. It's from 0 to xc dx. And with this part we have that actually we confirm the same. We confirm the same. T1C must be equal to TC because we have the same expression, and that's why we already see this result when we were saying that this was like symmetric. We say this was symmetric, so this one we have, but so that no that result we already have it, but in a more like we use the figure So usually we don't trust in this in more too much on those ones. But now we have expression on both sides. So now we prove with those that are actually the same. So it's just to be to be sure about that. Okay, why is this here? Okay, with those I have that result. What do we obtain? What do we obtain at the end with those? With that? Well, with that we actually obtain the same. The next, we already say that we are, for example, we are working with a solution XC. That solution XCT with a C anyone we wanted, right? So now let's say that, for example, we have the following properties because all the things we already say because of the boundary, how do I say, the boundary condition we already have of the problems, uh, right here, this one, we know, or we should know, that the xc from on 0 will be equal to 0. This one is important. And also bad, because in the way how we describe it, the 0 on the x prime of that solution, and this one on 0 will be actually equal to yc. When this one is actually bigger than 0, how do I say that? Well, we have those. We have those to prove that part there. The if you don't see right, I mean the points right here and right there, which are going to be the things that we are going to put it right here. This one I call it 1. This one I will call it 2. The 2 is going to be the point in the middle. That one right there. But also we have this one, this right here. For example, for the solution, if we are going to be talking about, we say this is half the time right there. So TC, what is going to be equal? Well, we already know. What is this part right here? XCT. This one is going to be, as we describe it, this one, the solution was XC. And now, the X prime C on that time TC, this one right there was 0. And lastly, then the last the last condition we have, that was XC over, it was on the end, and the end right here is actually the, well, I will do it this way because TC plus T1C, but actually we know this one is actually TC times 2. I'll call it just TC times 2 to make it. And actually we are more with this version right here too, TC times 2, because we are just saying that way is simpler to us. And this one also is going to be equal to 0 in that point, and x prime from that in that point 2 times TC. This one is going to be equal to minus y. And this one is actually going to be 0. Yep. Okay. Mm. Okay, this is actually one kind of detail I need to mention. and they have this one some notes. Usually, when we are keep working, where we continue to working, we are actually going to call this 2TC as B. They are calling this way. Yep. So because of that, yeah, because of that, value deployment, so secondary value deployment is positive. Yep. Usually is like normal to call to see this part right here. It's not like a big, not that big deal. Okay. Okay. Now, let's consider, for example, now we have a different theorem right here. The solution as a, well, not the solution, the proof, as we can see here, is actually pretty simple. I'm going just to write the little details, but actually, as I said before, it's actually pretty simple. They say, let C be such this curve different from the empty set, a closed curve that does not contain any singular point, and if C satisfies this expression right here, we say, as we said before, B was, what was B? 2 times TC. Okay, that satisfies the expression right there. So then, the function xct is solution of the boundary value problems, and that expression right there, the 13.1, is actually, if I remember correctly, let me verify. But yeah, if I remember correctly, that expression right there is just this one. Okay. So they are saying this one, the solution XCT, is actually a solution from the system. Okay, that one looks like a 6. Okay. Well, now we have that. What do we? What now? Now what do we do? Well, we already know because of the previous expressions. We have TC is actually 1 over 2 from 0 to xc dx over the root of c plus fx. To make it more consistent with the expression we have in the theorem, I'm going to put it in the same way as I'm going to put it as fx plus c. Is convolutive, so we don't have problems in that part. Okay, that's what we have. We also have b equal to 2c. So what do we have now? We have this one is equals to b, right? Yeah. So let's make this one. TC. So b over 2. And to make it even faster, I will put this. I will pass this to the other side. This part don't change, so I will put the same. And in this part right here, it's pretty easy. What we need to do is actually we are just going to do this. So we actually have the same we have here. Can go down. Okay. we finally obtain that expression. It's not that big of a deal. The expression is dx plus c. Okay. With this one, actually the theorem is proved. Now let's okay. This one. Now with this theorem, it also goes from a. It also we need to call a remark. I'm going to put it right down below here. In this remark, we say we have like two parts of the remark. First, we have from the, for example, to the if we have the equation and we consider, for example, a solution. Yeah, the equation we have is b equal to 2k dc. That is the equation we have. And because of that, the solution actually that we have must be or goes from usually C, but we usually we have a C, and now we are going to have like a CK with K that goes from 1 to 2, all that stuff. Okay. Now with this we find a solution, but the solution won't be an XC as usually we have been reading. We will have a solution that will include a CK very badly. CK. Okay. This one, as always, is the independent variable is t. Okay. And this one also will have like change signs from k minus 1. Okay. Because the way the count is, I mean, 1, 2, okay. Now, what do we need to mention from this? Well, we need to mention, I said before, this one will change the sign from k minus 1 times. For example, in the case of, for example, let's consider this solution right here. Let's consider, for example, we have a ck, we have the derivative of this, for example, in 0. What we previously have, I think I've already in here. I usually have that y over there. Now we have that y right there, but we will have yc, but also ck. So now, for example, if k equals to the solution, let's consider, for example, if k equals to, then we have the curve, well, the solution xc2 t. And now, and also we are working with this curve right here. We are not working with this curve. We are actually saying this, but now we say k is equal to 2. Right? Now, so with this case, we have, because for the positive, we will have that our t will go from 0 to the 2ct to c. This c, as I said before, is c2. This is the positive part, as I said before, from the curve. But also we'll have like a negative part that will be this one right here. As I said before, the first part right here, it was not the curve at all. I mean, all the curve. it was just the half plane of all that. So now we have a positive part and a negative part. So the negative part will be given by the values of t, where which comes from 2tc2 to t, specifically 4tc2. Okay. Yep. And also because of that, specifically, we will have, because basically as always, the derivative in 0 is going to be bigger than 0. Okay. That one is one result. But also in the remark, they also mention something different or something else. They mention, for example, let's consider a one system or one problem with the boundary value problem, as always. For example, we have this system right here. We have x prime prime equals to fx. From here, we don't change anything, but we don't have, usually we have xc, well, x0 equals to x evaluated on b, this one equals to 0. But now let's consider, or let's change this one a little bit. Instead of in 0 in this part right here, let's put in an a. Because of the previous results and all the stuff, what do we have? Well, we at the beginning have like b equals to 2tc, because at the beginning this part right here was 0. But now we are changing that aspect from the equation. So what do we have right now? Well, instead of being b equal to 2c, we actually, instead of that, we are doing, we're like moving a little bit this. So we have, for example, let's say we have a solution for the change signs in a chi -1 times, -1 times in an interval from a to b, as we have in equation, right? Now, our time, as we say, will be in the next way. B minus a, okay? This one is going to be equal to root of 2 times k, the integral from 0 to x0, xc, dx over the y we already know. Well, this is not the y, this is the root fx plus c. Okay, that's a change we do when we have that part. Also, we have the, for example, that we need to have this part for a solution when the solution have a c, when this one is actually a ck. Where k goes plus 1, 2, and keeps going. Okay, yeah. That's actually like the other part of the remark. This one, like right here, we usually no, we are not going to use it, because, for example, right here with the book, they mention one example, and I actually going to make do it right here, uh, just because I consider important to know how these kind of problems are actually going to be resolved, right? So, for example, let's say we have a problem. This is right here, and then they they want to make us prove that it has infinite many solutions. Okay, first one, what do we do? We usually work in the case, for example, in a curve. See, also with the equation, we don't change this aspect of the theory we have before. Y plus, what is the, well, I won't change this one right here yet, not yet. I will do it as this was minus, plus or minus. I don't remember right now. I moved this a lot. Minus, okay. Minus the big F equals to a C. Okay. According to what we have from the beginning, if x, the big one, was from 0 to x, the integral of the little one, dx. Sorry, this one I always forget. That's why I say I usually mess with this one. This one is fs and ds. Okay, but according to the way we describe the problems or the form of the problems or the systems, we say that, let's go up here again. This one is our fx, right? And in our problem that we are trying to solve, we have x prime prime plus 4x equals to 0. When we move the x prime prime to make that it appears along the equation in just one side, we have minus, right? Yeah, minus 4x. We have this expression, and this expression is actually going to be equal to the fx, the little one, the little f. So yep, with this one right here, we already know like we know how is our function going to be. What is the function we need to work. So now we obtain these fx. So what do? We integrate, and to this we integrate. This is from 0 to fx of minus 4x. Sorry, again, and to this next the same mistake. Okay, this one because it's actually from calculus previous courses. I'm just going to do it quickly. I'm not going to stay here a lot. This one is going to be just x over 4 minus 0. In the other, in this one case, we have this, and the other we have 0 because we evaluate. Okay, that's our fx, the big one. So now we continue with the curve. What is the form of the curve? Well, we have 1 over 2, 1 over 2 times y minus, minus, we make it plus, and equals to a 0. Well, not a 0, that one is a 6, not a 0. But this one should be bigger than 0. That is actually important, and also, as I said before, this curve should be known different from empty, from the empty set. Yep. Excuse me. Okay, let's continue. Yeah, we have the theorem, the previous one, which one is this one right here. We have this theorem, and actually we have that form, and also we have those because of all the theory we have from the beginning. So now we are going to use it that because we actually want to know this part B right here. So coming from that, we have that, and also because in this part right here we have me, we don't have, excuse me, we have 0, we don't have an A. So in this part right there, we got the B. We just copy the expression in integral from 0 to xc dx, this one right here, and this one right here is yeah, is fx. I will put it this way because I will put it later. Okay, if x, we already say, is minus x times 4 to the 4 is to the okay, c minus. Okay, that expression we have. Now, we also mentioned, we need to mention that k goes from 1 to 2, 3, all that stuff. Okay, for solution C, to ck, all that stuff we already know because of the remark. Also, now we use the remark just to say with the remark we have this expression right here. Let's call this interval right here as okay. That's how we are going to call the integral. Okay, and we have c minus dx and okay. Now by proceeding to make to the with the equation, we have this one right here, the phi we have. This one will becomes in the next expression we'll have, and in this part right here we are just, this one is equal to b, this one is going to be the, so yeah, we are just moving the terms to make it easier for us to how do we obtain the things. Okay, yeah. Now, because considering the case, for example, that we have that the xc is a case of a positive solution from this x0 to the x4 equal to c, then we must have, or we will have, that this one right here, no, okay, sorry, I write it wrong. I just want to obtain this one is 60. No, this one is actually x. No, no more, just x. This one is the one is xc, because we have that is a positive solution. So this one is going to be one of the c we have in this, and this actually is going to be 4. I don't want to express it in that way. I'm just going to be in this way. Okay, that's because x is going to be one of the positive solutions. We are going to be in this one is going to be the one is bigger than 0. Yep. So now, replacing this stuff on the integral we have here, we will have the next thing. I remember this one as something from statistics. Sorry. This one is going to be from 0 to, as we said before here, c1 over 4 is c minus. Okay. Now, let's notice that in this case, this part of right here, the c minus, this right here is actually going to be bigger than 0, or well, bigger or equal than 0. And this one, because this one's for the cases, because we have this right here. This one, when x is goes from 0 to the xc. Okay? When x is when x is in this interval, well, we have that this proof. I mean, this difference is bigger than 0. So according to that, well, and also that this one is a clear solution and not this xc must not be how do we say it? Singular point. Then because of that, we have that expression because that right, we are trying to prove this one is actually lower than infinite. Its name is finite. So now here, what do we have with this? Well, for example, with the expression right here, for example, let's make one change of variable. In this paragraph here, let's consider x equals to c 1 over 4 times c times a zeta. Okay? When we divide this to make the change of variable, we have the next thing. Dx will be equal to c 1 to 5 the zeta. Okay? With this one right here, we have, for example, well, we find or we replace all this stuff in our integral right here. So we will obtain in this paragraph here, this doesn't change, this one change, and this one change. This one all are the only ones that actually change from this. So what do we have, or what do we obtain? Well, we obtain from, okay, excuse me, I am actually wrong. This one actually change. This one goes from 0 to 1. And dx, we say already that dx was the c 1 over 4 d zeta over c minus, and the x, this one was equal to c 1 over 4 zeta, and all this we need to put it and multiply it 4 times. So we do it this, which is going to be equal to the integral to 0 to 1 c1 d zeta over the root of c minus. This time 4 we also have c, and this will have zeta times. Okay. As a beginning, we can do in this part right here. Yeah, we can do it. We can put this one outside of the expression in this way. We have 0 to 1. In this part right here, we have minus. No, this one is not minus. This one is positive. This one is going to be just a number. So we will have, but we are going to be, this one is going to be minus 1 over 4. This one is going to be d zeta. This one is going to be because of the common factor we have. In the first one will be 1. It's going to be just zeta 4. What happened? I continue. Okay, let me see if this continue recording. Okay, everything is fine. Yeah. Now, with all that stuff, we have, for example, this one right here. Because of how we describe it, this one is going to be positive, and also because of that, we will say we have, if we apply the limit to this, when c goes to 0, well, then in this part right here, it's going to go to infinite. How do we know here? Well, this one is actually we see this expression in this way. So now, if we apply this limit right here on c, on when c goes to 0, well, because this is not a limit, well, in this part right here, this one will go to plus infinite. So this one is actually correct, and we don't need to prove it, right? And also, we don't need to prove this result because it goes from the same in the same way. The limit of c goes, instead of going to 0 plus 0, because 0 must be c, as we say at the beginning, must be, it cannot be 0, it must be positive. Now, if we make that c goes to plus infinite, okay, right now in this part right here, we'll have they will be equal to 0, this limit. How? In the same way we in this one right here. This one is just a limit that we already know, and we have already proved. 1 over infinite, we apply the limit. This is not a proven one, so we don't need to prove it. Okay? Yeah. Now, it follows, for example, that we consider, or we take every k we have. For example, we have those cases. For example, now we make this equation. Where was it? Where that was. This equation. We did this one, but we do not use that version of it. But now we know, so now it will be easy for us to understand how this expression should be going. Um, I don't know the translation for that. So, for example, if we have this, I will write it again. We have this, and we have for this expression was positive. Uh, we we will have a solution. We will give a solution, for example, to the old policy that we have in the all that part in this example then is going to be lower. Okay, so with that, for example, if we give a solution as ck, that one is actually going to be or give us a solution of all the system we are actually working. The system we are working, so just to remember was this one. We obtain the effects, all this. Okay. Now I'm going to introduce another topic that this book actually used to understand the boundary value problems. That is actually the green function. The green function, and this topic is not that long. Well, this green function actually give well help us to give us some information about how is the form of the solutions, or at least what we can use this function for. So now the first thing is how do we obtain it? Is this green function defined? Well, now for example, let's go from the beginning. For example, let's take or let's say that we have, for example, any, as we said from the beginning, this will help us to solve any boundary value problems with the time dependent or linearity, all that stuff. For example, but the first thing we do to solve this type of problems, for example, we take two functions. Let's say, or let's call it a p and one r. Okay, this one is p, this one is r. Both not those two must be positive. Well, p must be positive. R can be is enough with that just being not negative. Okay, both of them must to be continuous, and the first one, the p, must be also dimensional in the interval a and b. This one is what actually we have in this part right here. Okay, now let's make with all that assumptions we have with the way we describe the functions p and r. Well, there we have, for example, the differential operator L, as we have here, that in the same way it's defined here. Let's make it bigger just to understand a little bit better. This is the function R, this is the function P. This will be times dx dt, and also this one is going to be derivated also times over t, as we can see in in this expression. This one, all this is going to be the linear operator. Okay. Now, because the operator is going to be linear, as a definition, we have seen this in the courses of function analysis. We have seen this because it must be continuous and yeah, it's the same one as being continuous and being linear. That, that's actually the same way you have here is the definition. Now, call it C1 and x plus a C2 x. No, this one is going to be needs to be g. Excuse me, y. Then, because this operator needs to be linear, then the result for us must be, excuse me, let me put a little bit better to not mess. This one must be, this one is a C1 L x plus C2 L y. Okay, this is what we meant in the linear operator is also y. With this, we also introduce about the, for example, according to the expressions or according to the results we have. For example, we need to use, for example, according to all this. Now, for example, let's consider the system For example, we have an L, an L, this will be numerator plus x, this one equals to 0, from t, that goes from a to b, and actually, in the same way, this one is going to be x evaluated on a should be equal to x evaluated on b, and this one all this equals to 0. In this part, the book assumes some results, for example, that nothing that we haven't seen on the books. So I'm going to pass all that part. Okay. Now, the book also introduces some two solutions that we must have it or obtain it by having will be a solution of the Cauchy problems that we have in the system. And how are going to be these solutions? Well, the solution they are calling it, they are just calling phi and this one phi. Okay? Yeah, they are calling these two solutions. Excuse me. And they will have these properties right here. For example, if we call L of phi, then this one must be equal to 0 for all t. I mean, every t we must have from A to B. Okay? This one of the properties from A. And also, it should it must follow the thing that actually if we do the next, if we evaluate that phi in A, we will have that this one is going to be equal to 0. But if we derivate that, we will have this derivative of this on A is this must be equals to an alpha, I did wrong, different from 0. I mean, it's important for us to be from this is different from 0. Okay? The same goes for the other solution. For example, I mean that we must have that L for all t in this interval A and B, and in this case, we now take the condition of B, we consider 0, and also the derivative of this on B, this one must be different from 0 also. We take a beta, but different from 0. We don't know yet what is this beta, but we just need to know, or we must have that this one is different from 0. Okay? Yeah. With this one, we are actually going to introduce, well, not introduce, we'll just clarify some details. For example, now, let's say that, for example, it's important to us that, for example, in the case of, let's consider first this one. Let's put it down here. If we consider that one, we must say, for example, that this one right here shouldn't be equal to 0. Because what happened with that? Because of okay, yeah. Notice this one should be different from 0, otherwise, no. Okay, yeah, that's why. Sorry, I messed up a little bit. Okay, we already know because the way we define that solution, we know this one also. What did I do? Okay. Sorry about that. We already know that we define this one as, in A, we define it as 0. I mean, it's equal to 0. So, for example, let's consider what happened when, if this one will be equal to 0. Let's consider what happened. Okay, now, as we say, the L of E was 0. All that, the points that goes from A to B, and then also we have it that phi on A was equal to 0. So now we have these 3 right there. So on all the interval we have 0, right? But now this one is the problem right here. If we consider this, we now this means that actually the eigenvalue that we are taking for the eigenvalue that we are taking for this operator L, this one means that the eigenvalue should be 0. But this one is not correct because this one Lx, as we say here, is equal to 0, but this is equal to 0. So what is this? This one should be equal to 0 also. But this, if this eigenvalue is equal to 0, well, actually it does not make sense. So that's the reason why we don't take this one as a 0. We try to make this one a different from 0. The same goes from when we are taking the other function or the other solution for the Cauchy problem. So with that being the case, we now consider about the Wronskian that we actually have seen since the beginning of the courses of the, I think, in the differential equation once we already saw these ones. But now we are defining it and we just say it, for example, let's say WT, and now this one Wronskian will be defined in the same way, in the next way. Phi of t, and the derivative of this on t minus the derivative of this on t times on t. Okay. This one actually is going to be the Wronskian, and we actually, to make it easier for us, we may say that this one is going to be equal to a constant that we will call it C. It's a constant. We don't know what, but it's a constant. We just say C. Now, by definition of how we treated the phi and the other solution, what definition I am talking about? Well, I am talking about of these ones. For example, phi of A was 0, and I'm talking about these two. I am talking about these two ones. So now, let's say, for example, we have to be more specific with this. For example, let's consider this equals minus C, that we say that was a constant. We say that was a constant. Yeah. Now, let's evaluate this function on one of the 2 points. I mean, in A or in B, and let's make sure that this actually goes different from 0. That's what we need to make sure from that when. That's what we need to make sure. Okay. Now let's do it. The WA. Okay, and now we just replace in this part right here. I'm going to do it right here. In this part right here, in the first one, because it's phi of A, this one is going to be 0, so all this is going to be 0 minus sorry, excuse me, I forget to replace. This one is A, this one is A. As we say from the beginning, this one is different from 0, and this one is actually, we say at the beginning, this one was an alpha. So then, this is our expression, different from 0. We have it, because the alpha also we define as different from 0. Now, let's see what happens when we call it a minus c equals to w b. Now we are with b, okay? So we say this one should be different from zero. In the derivative from this one was a beta minus the, okay, in this one, in this part right here, this was zero. So okay, what do we obtain? We obtain p of v, this one zero times minus zero. Okay, all those ones different from zero, so we don't have problems in that part. Now, in other words, what we say with this? Well, actually with this one we are saying that these two functions, these two solutions are actually linear independent. That's why we want to know about this, because we want to know we are not talking about the same solutions. So now we are going to define about the green function is based on these two, in this old expression that, well, in this old function that we have uh, is based on the solution we defined and on the functions we already defined. So, and also this is green this green function we mentioned on one square. This square is actually going to be q. We call it q. Could be anything. Equal from ab times ab. Okay. Now this is actually going to be the way the green function is going to be defined. The green function is actually equal to, for example, we say, excuse me, a t, and we say an s. The t is the t we have because we know this part is autonomous, so okay, we don't have problems from the t. The s we now define it from here to the way we now prove the green function, because the green function is actually going to be divided in two parts, okay, depending on what we what we uh, what the parameters we implement, okay. So i'm I'm going to do this one a little bit bigger, because it's a little big. Okay, now this ring function is actually defined. I'm going to be the one of the parts of the function is 1 over, we consider the function p, the first function p that we defined from the beginning. We say the c. The c is the constant we defined for the Gaussian, and then this one multiplied by the two solutions. But one solution is by t, and the other one is to s, evaluated on s. Okay? This one, this expression is going to be valid when? If goes from A to S. Okay? Now, in the other side, I mean, when the t goes from S to B, we have basically the same this part right here. This part right doesn't change, but the part that change, or the one that is easy to memorize, but what's the only what's the function is this one. We have this one is S, and this one now is going to be t. Also, if t belongs to S to B. Okay, this is how I'm going to write this one letters because I don't understand it. Okay, that one is a function all the way is fine. So now we have, for example, that this function g is actually going to be, for example, continuous on the square we have. Okay, first one is going to be continuous. We don't have issues on that part because first we have p is continuous. The two solutions are actually continuous, so we don't have problems in that part. And also, we want to be sure from this part right here. For example, let's consider what do I do? Okay, I do nothing. Let's make G an evaluator on A and in 1S anyone. We right now we are not considering S because S is just a variable that S should be in the middle of A and B. If S is not in the middle, well, actually this won't make any sense. So now, if you evaluate it, we will have phi A and P evaluated on A and C. According, because say P of A, we say phi of A is actually 0. Then all this one is actually 0. The same goes when we evaluated this one on B. When we evaluate it on B, we will have BS. Then we use, because we are actually talking about, for example, if we talk A and B and 1.S, first one we use this part right here. Now we are talking about this one right here. So now we are using the second function. So we change this part right here. This one is going to be phi of S, and this one is going to be of B. And this evaluation in B and C. Because this expression right here is actually equal to 0, then it's also B. This one looks like a bigger one. Okay, so then both expressions are actually equal to 0. So in that part is not the problem. Okay. Also, we have this expression, the g is actually differentiable in all the in in this interval at ts in in this square. But the only point that actually is not differentiable is when s is equal to t. That's, I mean, for example, when we consider this point right here, we are actually saying that this one is actually not differentiable. But in all the other cases, we have that it actually is. Now, with all that introduction for the green function, we are actually going to do an example of how do we obtain it. Well, for example, right here, I have an section, no, just down here. For example, let's calculate the green function for this one right here. Let's say the operator is Lx equals to minus x, and we are working on the interval that goes from 0 to 1. Okay. Now, let's go to the beginning because I'm going to make the point of something. We have to say that the differential operator was actually defined by this way. But how do I move this one? Well, I don't move it. I will say it that way. Okay. Well, better I will write this one. Yeah. Okay, is x minus x. Okay. The first thing we want to know is what is our functions, the function p and the function r. So what do we do? Well, we find it according to the differential equation, to the differential operator. The way it is defined, well, r, we have x. The r should be next to the x. So here we have a 1. So now we have r is actually 1. Now with p we have a little bit different. Well, a little bit difficult, but it's not that difficult. With p, we actually say that, for example, this one also will always give us um, second order derivative of x, but we want to know what is here. Well, if we notice, this one right here is actually x prime times a p, and then we derivate this, so we should obtain an x prime prime times a t. If we have that pt times with okay, now then we apply all the derivative rules that we know. Okay, but if we have that, for example, or p or pt, instead of being having variables, it's just a constant. For example, then or p, for example, we consider a constant, then or on second variable will be x, will be this case, right? We don't move a lot. So what do we have? If we have that our result is here, and the only thing that is going with the x prime prime is a number and it's 1, well then we have that p is equal to 1. That's our logic. So now let's go down again. Right here. Okay. So now with this we have that r, our function here, is actually going to be 1, and our function p of t is also be 1. Both of them are going to be constants. They don't have variations according to the independent variable. Okay? Both of those are going to be defined on the interval 0 to 1 in the same ways as the linear operator, the differential operator, excuse me. So now let's say, for example, that we have this expression right here. Okay, yeah. Now let's do the usual. But how do we obtain solutions? Because we need to know what are our solutions, three and our two solutions for the Cauchy problem. So we need to solve this differential equation. So we already know some methods. So let's just apply those. And let's have, for example, let's do. What are you doing? Excuse me. Okay, nothing happened. Let's do this one. Now we are trying to obtain the solutions, right? Okay, then because of this and the type of problem we have, the solution must have this form, or usually have this type of form when we are with this type of problems. We have that our solution should be or x of the solution must be equals to a c1 t plus c2 minus c. Yeah. Yeah, this one because we at the beginning we obtain the eigenvalues, values, so we have those. Okay. Now we use, for example, our what we usually have for of the conditions. So usually as conditions we have that x0, x in this case usually is b, and now we have is 1. This 2 should be equals to 1, to 0. So then, if we evaluate it, if we evaluate these ones, we have C1 and this part right here. So, okay. This one actually is equal to 0 because we say this. This one looks like overdone. Okay. So we have this equation right here, and also we by doing this, yeah. But first, let's don't hurry along. Then we have the derivative of this, and let's consider in this case, in this part right here, we have C1. This one doesn't change because the derivative of this doesn't change. Here we just change the sign of the expression. So at evaluating on 0, then we just have minus C2. Okay? And this one actually is going to be equal to 1. Okay. With these two expressions, we will have a way to like looking for one in this way. I mean, we try to obtain one of the results. So C1 should be equal to as I said before, this one was obtained from this, and in this right here we have 1 plus C2, where C1 was actually equal to minus C2. So with this one right here, we obtain C1 is going to be 1 over 2, and C2 is going to be minus. Okay, that's the result we have here. Well, in this part right here, I did it a little quicker. This one is just 1, but this 2 goes down, so okay. Let me do it a little bit clearer. Okay, yeah, we have those results. Oh no, no. Um, A little bit. Okay, I hope this works. Well, now, with those being obtained, well, now we just replace those in, well, no, with those being obtained, yeah, we can take, for example, we take the two solutions. For example, we say that phi will actually be 1 over 2 from minus, okay, and with all that, also we say how this one move. Okay, here. And with these ones, I say our bar phi this one is actually going to be in the other way. Well, actually should make the process for this one. And we have this. We have the first one, the phi, the just phi. Okay? But now, for example, we have, for example, in the case of x being 1. So now, if this is the case, this should be equal to 0, but because of C1e plus C2 over e, and if we consider the derivative of this, now, this one because of, this one was for the phi, now we are considering the other extreme of the interval because it was 0 and 1, okay? Now, because of that, we also are using the same solution. We are just giving them values to them being more specific, okay? Remember that the first one, the phi, we are looking for that one was 0 on the value a, and the bar phi that we are looking for that this one is 0 on the value b. Our value a is 0 and the value b is, our value b is 1. So that's why we are making this one, okay? Now, the derivative of all that stuff is actually From E we don't change, it don't change, it remains the same. And from the other one, well, actually it doesn't change a lot. It doesn't change a lot either. Just keep the same, but they change the symbol, the sign. So it gives C2 over E. Okay, and this one also being with this one being equal to -1. Okay. Now with this, we repeat the same process. I mean, for example, with this one we have C1E will be equal to minus C2 over E, and we also have that C1E is equal to -1 plus C2 over E. This one is going to remain the same. And I have that, this one right here. So I have C1 is actually minus C2 yeah, right. Yeah, with all the stuff we just replacing. So we have C2 minus C2 over equals to -1. This one is minus C2 is, that one is, that one is there. Let me verify. Yep. And with this one, with those, C1 is actually going to be minus over 2. So C1 is actually going to be minus, this one is okay, I'm right? Yeah, I'm right. This is going to be my constants from the Murphy solution. So now I'm just replacing those, and I obtain that my second solution will be, both is negative? No. For the first one is -1, and this one multiplied by E times D, and this one, the next one is plus E times 2, is over 2. And this one is actually negative. So yeah, that's our second solution, which actually can be a little bit more synthesized. Yeah, those two can be more synthesized. Yeah, this one actually, the first one, is the definition of a sine of t. But this one, the parabolic one. And the other one, I think is actually the same, because this one is t minus 1, and this one is minus t plus 1. So if we change those, I got 1 over 2 t minus 1 minus plus 1 over 2 e minus t plus 1, which can also be minus. Yeah, according to those, well, according to those, this function can be synthesized as, yep, minus sine hyperbolic of t minus 1. Yep. Those two are my solutions, my Macaulay solution for this problem. So now, well, these two are two different solutions, so and different functions. So these two are clearly linear dependent. So now we just want to make the form of the TS, GTS. So let's make it now. So we know T is actually 1. We know the form of the phi and the bar phi, and we know no, we don't know C. We need to know about C. The pronunciation of it. C should be actually, because of the way we define it, this. I will say this one because where did I say it? Here. No, here it's not. Here, right here, it is. This one right here, we say that it was 1, so it doesn't change. So we just look like for the other result, which is 0, or A is 0 right now. So now we evaluate it. We have that sine of flows evaluated on 0. Well, I rather evaluate in this way, which gives us plus it cancel. Okay. Now this one is actually going to be equal to different from 0, so it is okay. It's okay. C1 is that minus, yeah, that is okay. Okay. Now we have the C, we have the P, we have the phi, and the bar phi. So we don't have any other thing we have to obtain to get the green function. So now we just need to write it. The green function, as we define it, should be equal to Ts and S, that is in between on the interval 0 to 1, for P is, the function P is 0. The function C, the constant C is this one, and we already know that is hyperbolic sine of T and hyperbolic sine of T minus 1. So in the first one, we are saying that is C, so this, in the first one, I consider first the case of if T belongs from 0 to S. And it was the case of first the sine of T times sine of S minus 1. And the other one is sine hyperbolic of S and sine hyperbolic of T minus 1. This one, if T belongs from S to 1. How long is it? Okay. To don't go that long with this, I'm going to do this last theorem, and with that I'm going to end this part of the video. I'm going to end this video. Okay. Now, and this is the part important of the study the green function is because we are at the beginning. I say we need to understand this part to know how is a possible form of a solution, and that's what the theorem says. For example, they say let's consider for any continuous function h of t, such that the non-homogeneous problem that we the problem that goes. This one is a theorem, just that I don't put the image. Plus hc of x equals to 0 from t going from a to b as always. And then the same condition as always also, x evaluated on a, x evaluated on b equals to 0. Then we can say that this has a unique solution given by the function. Our function will be given by x of t, this solution, and the integral from a to b of the green function that goes, as always, ts, this is the parameters, and also the function, hs, and ds. Yep, that's our theorem. Now, the proof, in this proof, actually we can say, we can do as always, but in this case, actually, we are going to use some details to make it a little bit easier. For example, we consider P as 1 to don't make that, because as we can say, if or P, this is just C, but if we will add a P different from 1 in this expression,
it will be a little bit more difficult for us to obtain our function g. So to avoid that, we are going to consider in this function p in this theorem, we are going to consider p equal to 1. Okay? Now, that is a constant. Now, let's consider, for example, that because as always, x of a is actually equal to 1, but sorry, equal to 0, and also x of b actually equal to 0. But we are saying that, for example, that is the way that is the form that all the solution has. So let's make sure that, for example, it verifies for that 2 points that we already know. Let's say, for example, let's consider xa equal, that goes from, in this case, from A to B. The only part that here that evaluate a point is in the green function, that is g a s h s ds. But we know by the previous results that the green function on the both sides of the interval, I mean on A and on B, those sides are actually equal to 0. So what is the result here? The result here is actually going to be 0. So we have that these 2 points verify. Both of them. You know, on B it also happened. We have A, B, G, this one B, S, H, S, DS equal to 0. And both verifies. So now, let's prove, for example, that it verifies for the desired boundary now, we have, for example, that for different results from different courses of analysis, calculus, all that we have using this stuff. For example, we have an integral that goes from a to b and dx. We say that we can separate that interval if the interval we have is continuous and all that stuff. Okay, so now we can separate it as usually we can do from a to 1s. Any s we have, any s we want, right? And we do the same, plus this will be equal to ds to the b. This result right here will help us to obtain our results. Okay, excuse me, sorry, I missed something. Because we are not evaluating on S, we are actually evaluating on a point T. We are separating this on depending on the point we are going to evaluate. So we are separated on this one. That is actually it's impossible because these points T are in between of the interval, so nothing changes. So now we are saying this, we are now changing that interval that we have at the beginning from the x of t from the solution. We now modify a little bit, so we have the x of t will be from a to t of the same goes. This is not h, this is s. This one is actually s, h, ds, and this plus from t to b, and this part right here is still t, s, hs, ds. In this part right here, nothing changes at all. Basically, it remains the same. Now, we can evaluate the two parts of the integral, but now, for example, let's consider the cases of, for example, in the first part, right? I mean, for example, let's consider in the case this happens. this actually happens. We have A, S, and T. Okay. Then we have that our function, actually the green function that we have will be given by this one is going to be given by the second expression, because our t that we are evaluating is bigger than the s. So it's the second expression. It's the second part, as we say from the beginning. This is one s. This is the first expression. This is first expression. We are using this one. We are using this one right there, because how we are taking the t. Okay. So we are given the green function by, excuse me, this one is t, by p is equal to 1, so no big deal on that. It's just 1 over c, and the other part is phi. This one is s, and the bar phi is of t. And now let's consider the other possible example. The other possible case is, I mean, that if we have t, this is the other possible case. This is the first case scenario. The first scenario. This is the first scenario. Second scenario. And this one, we are taking the first part of the green function that we define. So how is it going to be? G Ts equals to 1c, because green p is equal to 1. Phi is going to be evaluated on t, and bar phi is actually going to be evaluated on s. Doesn't change much in right here. I mean, it's just previous result that we already defined. Now, let's rewrite the same expression of the integral we did right here, but changing these parts right here. How do we do it? Well, let's do it in the next way. Okay. This part is going to be a little bit smaller, because I think it's going to be a little bigger, the expression. Okay. The xt is going to be equal to, okay, we are integrating in base of s, so the t is actually considered a constant right here. But let's say a to t, so the green function is the one that we are trying to replace. In this part right here, from 0 to t, what do we have? Well, in this part right here, we have this expression right here. So phi of s bar phi of t, and this one multiplied by the h of t. Sorry, this is not t, this is s. ds plus t b, same goes, the same goes. So t, this one is on s, this one is still on s, and ds. Okay. Then, with all that, now we have that our solution should be actually, and because of the way we usually we can we can derive this expression, right? Now later we will get the point of where we do this. So now, okay, first this expression can be out of the integral, and also this integral, because we are integrating about in order of s, so not in order of t. So now let's consider x prime of t. Because right here we are integrating in sense of t, not in sense of s, this part right here, it doesn't change that much because this is the only term of t we have to be integrating. So what do you obtain? Well, you obtain the following. You obtain that is, for example, and this multiplied by a from t to t of 1 over, no, I will do it directly. This one is over c. And in the other part, we go from plus this term doesn't change, and now then we derivate all the other part. This one is actually out of the integral. To be a little bit more clear with that, I'm going to write it down here. I mean, xt is actually equal to yeah. This is the terms that we are derivating. Right here, we do the derivative of the first one now, and the second one goes the same. Now, the first one goes the same, the second one is derivated. Okay? So, first one goes the same, the next one goes derivated. So, in this part right here, we have we the derivative of the same of an integral is the same function that we are integrating. So it doesn't change a lot. It's just that we are evaluated on the point t. So we obtain this one is over c, and phi of t, h of t, nothing more. Now this one on the other part, it goes sorry, this is no plus. And lastly, okay. Yeah, in this part right here, because of the way we have the integral, in this part right here, it's actually not plus, it's minus. So, because of that, these two terms actually can go. So at the end, we just stay with the first two. Okay, we can stay just with those. So now, we don't want to take only the first derivative of this, but we actually want to know because of, what is the theorem? Because in the theorem, we have mostly about the x prime prime. So now what we want to take is specifically the second derivative of those. So now we derive this. This part, we do it in the same way as the first one. And in this part, the only thing that I think that changed a little bit is, no, in this part it's always the same. This DS should not go. All this over yes, sorry, over C. Also this. Okay. In the last one, we eliminate those two terms, but in this case we can do that because these two terms are actually different. So what we do is we do the common factor. The only common factor we have is the h. Sorry, yeah, this one is t. Sorry, I write this wrong. T and t. So we do common factor on those two terms to get a little bit more easy expression to manipulate. The common factor of all those two should be 1 over c times hc, and in the first one is and the second one is okay. But now this part right here at the beginning of the, well, when we were defining the green function, we say this one is actually the Wronskian of, yeah, here. So now this one actually is going to be equal to minus c, right? So what do we obtain at the end? at the end, we will have that, for example, 2 over c
or x prime prime. The first two terms goes equal, doesn't change, but in this part right here, we have 1 over c equals to minus c times ht. So
all those terms reduce to minus ht. Okay? Yeah. Now, why was the reason to obtain all that stuff?
well, because at the beginning, when we were looking for this, we had the we have the differential operator that goes Lx, and by definition,
Because we say p was equal to 1,
we have this is equal to x prime prime minus 1 times c minus, and r, we don't say that r was equal to 1, we just say
r is, we don't know, actually,
and this one
equals times x. So, now let's see what gives us that.
we know the expression for this, and we say that we only don't know this one.
This one is just an x. So,
Let's see how
this gives us the results.
this gives us the old equation of, the first one is a and b is h is ds c plus this one is a to t, this is t to b. And this one actually minus ht, which we had from before, and minus rx,
The new one. With all that, we actually we now say, because the way we define the green functions, what was the way we define the green functions? Well, not the green function, the Cauchy solution that we define for the green functions.
for example, I mean the phi and also the bar phi.
We define with properties, and specifically that these two
Actually,
should be, in this case, be equal to 0
from t that goes to a to b.
both of them have that property. So now,
What is the case of the linear differential operation,
differential operator,
of
this this one is
actually minus r phi, right? This one is actually equal to 0, and
what do we obtain from here?
well, we obtain that will be equal to r phi. So this one will be useful for us to replace this one right here, and for the other one, for bar phi, the same goes. So
This one will use for us to replace that part right there. So now we have that differential operator on x will be actually now replacing to it with bar phi prime prime. We now have here phi 50 obviously, and the integral is always the same basically. This doesn't change from 0 to t. This one in s, h in s. No, stay there. Okay, in this part it goes the same, so this doesn't change. No, this is minus, sorry. Okay, so with all that, we now say that this one is actually given by R. The in this part we are just using common factoring on those expressions. Okay, then we just finish with saying that we just include this one inside of the integral because we don't change it that much. And if we include this part right here inside of the integral, what do you obtain? We obtain at the end the same of the green function according to the according to the part of the interval that we are considering. For example, in this case, from 0 to t, and this from t to b. I will just put it directly because it's just to include this one inside of the integral because it's no is because it's independent it does depend on s, so it can go inside, and then it's the same of the green function, the same way the same thing that we defined already. So we have ts
and hs ds plus t t and b g ts hs ds minus okay. And just to end all this, we have, for example, as we say at the beginning, this just is, we can like, because we are talking about the same interval, we can just make just one integral from all this. So we obtain here equal to, from a to b, not a to t or a to b, a to t, or a to b, because a green function, we treat it this way because the green function is defined in two different ways according to the part of the interval that we are working in. But now that we already put that analysis on each part of the intervals, now we can already put it together again. Then this one is going to be actually going to be minus h minus x. Okay. And yeah, well, with all this, finally we have, for example, that as we say at the beginning, this one is what's going to be the this one is what was going to be our solution xc. So we replace that with that. So we say that, for example, now we have rx minus h minus rx. We have minus n, and we have okay, then sorry. Then finally we have, for example, because this one's all about this, and this one is actually doubt. Usually we define this expression. So because of that, we actually prove the solution of this solution, prove the existence of that solution xc that we are actually looking for. And also, we say that actually it verifies this form right here. I mean this, and actually the solution exists. And also that when we do that, for example, we take a solution, we say that we want to prove that it's unique. Usually what we do is that our solution usually is, we take two different solutions, and then we, for example, we have the setting, for example, I'm going to put it right down here. What we usually do when we want to prove that the solution actually is unique, what we do is we have for example, we have two solutions, x1 and x2. Then we want to prove it's the same. So now let's put these ones on x1 minus x2. Then our this one evaluating in our differential operator, because this one is linear, we will have this one. This one will be equal to x1 minus x2.
And these two actually will be equal to 0 because, yeah, that's what we say, we are talking about solutions. So, also, because these ones are solutions, zeta o evaluated on A will be equal to zeta evaluated on B equal to 0. But that is the problem, because we are doing that, or eigenvalue we are taking will be meaning that we are actually taking an eigenvalue equal to 0, and that is one of the problems from taking this. So from this contradiction, we are saying that our two solutions, the x1 and the x2, should be equal. So that is the thing about that. Then, to conclude about this, there is a last corollary about this, but it's only the same thing, but including something a little bit more. That is, for example, it says that if we take a continuous function that have f tx, and this is continuous, then our solution, our solution, well, then we have, for example, our problem, our system, that is this one equal to 0. This one as always. Then our solution for this will be given by, instead of being in the solution function h, we have now the integral from a to b of the green function ts, this one as always, but now instead of in h, we have the function f. This function on s, I guess, all this on by the ds. Okay. This corollary says basically that this will be the form of this type of problems, the solution of this type of problems. Okay. With this, I conclude the introduction for this topic of boundary value problems. I hope you understand.